So in 14.2 and 14.4, we're going to talk about types of reflection, specular and diffuse, a law of reflection. We're going to talk about additive colors for light, for color of light, not for art. We'll talk about the difference with art and light, like pigments and art. We're going to talk about the reflected color that you're seeing coming off of something, and then how polarization works. So first, reflection. Anytime an EM wave is redirected, it's called reflection. Have you ever been at home? And this is, I do this just to mess with myself, and I'm really such a geek sometimes, sorry. But like, imagine you're like sitting in bed or on the couch and the TV's there. Have you ever aimed the remote backwards and it still works?
Yeah.
I know it's stupid, but has everyone tried that before at some point? Why does that work? What kind of a wave do you use? Do anybody know remotes are act on what wavelength? Or tell me how it works for now.
Yes. Reflects off the surface of the wall and that goes to the TV.
That's it. That's all it is. Remote controllers use infrared wavelengths. Infrared. So when you're using an infrared wavelength, or when you're firing a wave on the infrared frequency, what's happening if you do like behind you, it'll hit the wall and it propagates outward. So that's why even when you like shoot backwards with the remote, it'll still get the TV. Okay, because the fact there. Now if you cover the sensor though, okay, if you cover the sensor and do that, obviously it's not going to receive it anymore. The other day I was trying to work my TV and I had like a glass filled with like, milk. I mean it was milk, yeah, because it was opaque. And it was in front of the TV sensor and it would not work. And I tried like bouncing it off, but I eventually had to get up and actually just move it out of the way because no angle was working. It annoyed me. Anyway, let's continue. So there are two sections, diffuse and specular. This is another topic like chapter 12 that's very conceptual. Okay, but it's pretty easy. That's the good part about this. Diffuse versus specular. Think about diffusion. When you hear diffusion in biology, what did it mean? When the cell membrane, like there was diffusion going on.
It like kind of just fizzed out.
Yeah, the actual thing, the actual concentration eventually kind of like dissipated, if you will. Well, with diffuse rays, imagine the rays coming in and going off like just anywhere. Because the surface, not diffuse rays, but diffuse surfaces. Because the surface itself is not smooth, it's not specular. Sun's rays come from the sun and they propagate every direction. But the rays that reach the earth can be considered to be parallel, although they're not exactly parallel. But see these incoming rays, these incident rays here, these are considered to be like parallel rays. Well, on a specular surface, how do they come off? How do they come off on a specular surface? If they came in parallel, they come off
Perpendicular.
well, perpendicular to the last one, maybe, but to one another, I'm saying. What are these? These are all parallel to one another, specifically, not to the rays. Yeah, this might be an 90-degree angle, it's possible, but not always, okay? The idea is this, though. If light rays hit a specular surface and they come off of it, they come off parallel still. Whereas diffuse surfaces, they come off at random, arbitrary angles when shined. This desk, although the color causes it not to be able to be reflected, but this desk would be considered diffuse. Just to give you an idea, okay? This is a diffuse surface. It is not smooth enough to reflect light, especially parallel. Now, this would be considered specular for sure. Absolutely specular. Okay, two different surfaces. It has to do with the surface quality.
Is that like why a mirror?
Yeah, a mirror is definitely specular. But a mirror, if you recall, is metal with glass on top of it. That's what a mirror really is. It's a layer of metal, a really thin layer, with a piece of glass on top of it. Okay, there's a little bit more to it, but generally speaking, that's what a mirror is. Talk about the angle coming in and the angle going off. So for specular surfaces, and this is one that I told the other class, I mean, you still have one extra credit right now if you want to do, don't forget, with the waves. Remember I told you if you want to create waves at home, create standing waves, measure the wavelength and all that stuff. You still do that in the amplitude. But there's another opportunity for an extra credit, but it's a lot tougher. Alright, the way you'd have to do this at home, because it doesn't work as easy as it's shown here. Like that'd be great if you just shine a light in the mirror and you see the reflection come off. What I would do is, if you have a laser pointer, be careful with it please though, please don't shine in those eyes. But you can shine a laser pointer off of a mirror, okay? And if you can do that at home, you need to hold it fixed though. So maybe put the laser pointer on like a surface. Okay? Hold the laser pointer down. If you can mark this location, you can mark the location on the mirror, and then you can mark another location. What you will notice is that the ray hits the specular surface and it comes off at the exact same angle it came in at. The law of reflection tells us that the angle of incidence is the same as the angle of reflection. Now, those angles are measured with respect to the vertical here, or the normal. Remember, normal means perpendicular to the surface. That's what the normal force is. The normal force is always perpendicular to the surface. So here, for this topic, when you're measuring theta, you're measuring with respect to the normal. Okay, to the normal. It's one of the rare times we don't use the angle down here. Alright? Now, the theory here again is that these are the same. That's all. So if you can prove that, if you can show that with some sort of a video capturing yourself doing this, and then some diagrams, I'll give you bonus. But this is not an easy one. It will take a lot of work. So I'm just giving you a heads up. Right, as far as if you want to get some extra credit, depending on how you did on the last test. But that's what the law of reflection is. That's all. Okay, it's pretty straightforward. It reminds me of, well, should I say that? It reminds me of geometry and also billiards. How many people have played pool before? If you hit a ball straight on and it hits the bumper, it will come off the exact same angle. Literally, this is exactly correct, assuming there is no spin to the ball. There's no backspin on the ball, which none of these things are really possible. There's always going to be some spin because it's rolling. But if it's just rolling forward with normal rolling motion and it hits the wall, the angle it hits off the bumper will be the same. That's how a lot of pool players are able to judge angles. If you're interested in pool, Mr. Haw is actually like a really nasty pool player. Like really good. Yeah. It's a fun fact. So if you're interested in pool ever, and you want to question him on it, ask him about his pool days. He'll tell you about them. He still plays. He plays in a pool league. He's so good. Like really good. Yeah. I was amazed because I love pool. I'm a big fan of like darts and pool, those kinds of games. And I love pool, but he would whoop me if I ever played. I thought I was good, and he would tell me about, he plays in this league, and he's telling me about these trick shots people do, and like hopping a ball over this, and I'm like, oh, I didn't do that. I never do that. But I just use geometry in pool. That's why I think I'm decent at it. All right, the visible spectrum. Stay on focus, guys. Please focus. The visible spectrum ranges from low frequency red to high frequency ultraviolet. We already talked about this, so I'm not going to go into a lot of detail. We talked about this a lot yesterday. But Roy G. Biv, okay, red, orange, yellow, green, blue, indigo, violet. Now, the important part that you get for right now is that you see what is reflected. Remember that. If you see blue, blue is reflected from that material. If you see red, red is reflected. If you see white, all the colors are reflected. If you see black, all the colors are absorbed. So you're not seeing any reflection. Now, does that make sense when you go to the beach in the summer? Why does everybody wear white shirts or light colored clothing at the beach?
No.
To stay cool. If you wore a black shirt, the shirt would absorb those rays. It would absorb all the light and it would be hotter actually. If you go, and Johnny Campbell mentioned this, if you go to any like Central American country, cars are traditionally painted white or like a yellow, like a light color. For that reason also. I used to play basketball at my house when I was a kid, and my dad built us a basketball court in the backyard. And it was just pretty much like a driveway, but he used asphalt, which is all black. Like asphalt, not concrete, different things. Asphalt's like tar, it's all black. So in the summer, we had a pool in the backyard, and I have brothers, so we'd always play sports. So we'd be playing like football and like jumping in the pool and then play basketball. But we could never play basketball barefoot, even though we'd always want to, because the court would heat up because of the tar. So we'd actually go into the street in front of our house and play. We had another hoop in the front. We'd play basketball there on concrete, because concrete is like a white gray color and it reflects all of the sun. So the concrete in the street was never hot, but the backyard, the tar in the summer was always on fire. So that was just like another fun fact for you, okay? I don't know, related to my life a little bit. Let's see if there's anything else I wanted to mention in this. Next, in paint and in art, primary colors are different than in physics. These are the primary colors of light, not the primary pigment colors which you know of. The primary colors of light are red, blue, and green. They are also the colors that you see when you're doing what at home? Anybody know? At home, there's a certain thing you might do that only use these colors, whether you realize it or not.
TV.
Watching TV. TV only uses these colors. Every pixel is one of these three colors. The combination of those pixels next to each other produces different colors. Okay? Now, you can also have the combination of red and green light giving you another color as well. The idea I want you to get from this, though, I'm not going to go into a ton of the physics behind the different light layers on top of each other of light, but the three main colors are red, blue, and green, and the varying proportions of them are what produce the other colors themselves. Okay? Your eyes also have cone cells that are able to be receptors of these three colors. So remember when we talk about color blindness real quick? The major people that are colorblind, it's either red and green or red and blue. You hear that a lot. Red and green or red and blue. I have a freshman, it's red and blue for him. My brother is red and green. He only sees green, he doesn't see red and blue. Or he doesn't see the red. Okay, so it has to do with not having that cone cell. So for example, my brother does not have the red cone cell in his eyes. So he only sees green when it comes to that. My student in my freshman class doesn't have blue. I think he only sees red. Chris Campbell is also, yes, that was another one of my students that had. All right, last thing. Last thing. Let's talk about polarization. For polarized light, guys, we have 4 minutes. I want to finish this. Where do you hear polarized or polarized light? Lenses. You hear that a lot with lenses, with polarized light. Now, phone screens or screen protectors or windshields on cars also involve polarized film. A TV monitor or a screen on a computer has a polarized film light on it, actually. Now, here's what polarized light does, or polarized layers does. And I'm going to explain, and I'm going to try and put in simplest terms. Look at these waves real quick, and follow on the board. Just take a look up. For non-polarized light that has not gone through a polarized lens, so light coming from the sun, for example, is not polarized, this light has random orientation to its waves. Follow the cursor here, please. The yellow electric field that I'm following is vertical. It goes up, then it goes down. It goes up, then it goes down. But this light ray, or this EM wave, comes out of the page, into the page, out of the page, into the page. This one is kind of at an oblique angle, back, and then forward, and then back, and then forward. So these EM waves are not in the same orientation. If you take this EM wave, watch, follow my hand, you need to see this. If I look at this vertical, right here, this up and then down, then up and then down, ignore the blue, just the yellow part. Take it and rotate it like this. You get this right over here. Literally take this EM wave and rotate it 90 degrees. The yellow that's going up now comes out of the page. So now it's coming out of the page. The yellow that was down now sweeps underneath and goes into the page. It's now into the page. So it has to do with the orientation of the EM waves. So I'm going to slide over now, watch. When I slide over, look at these three waves. Follow me again. Up, down, up, down. Again here, up, down, again, up, down, up, down. This is polarized light, where the orientation or the alignment of the EM waves is consistent or the same for each EM wave. When you have this, where they're all the same, this is called polarized light. That's how light can be polarized. It gets passed through your glasses or through the LCD screen or through your windshield, and it changes the orientation by realigning the angle it's coming in at through what's called its transmission axis. You don't need to know that term, but that's how it's physically working. So on a car, normally light hits the car, most of it goes through, but some of it comes off as a glare. Well, now they have polarized windshields, and those windshields don't produce glare anymore because it changes the light so that all the light comes through. When you're polarizing light, you're allowing the light to come through. Okay, for a car. For glasses, though, what do polarized glasses want to do for sunglasses?
it off.
Yeah, you want to reflect those light rays. So it's changing the light so it's not polarized there. Then for a computer screen, this is an interesting one. I'm going to hope that, I think Elliot was going to help me with this. He was looking into something with this. But for a computer screen, it's really kind of crazy. If you take off the polarized layer, all you see is a white background. Now, if you take that polarized layer and like say you put it in front of your glasses, you would see the screen. And then if you move the polarized layer away, you'd see a white background. I'll show you a video of it. We might actually do it here if you can get the supplies for it. But the idea for polarization is that you're changing the orientation of the EM waves to produce a desired effect. Whether that means reduce the glare or don't allow certain rays to come through glasses. Now, anybody have glasses on right now that are polarized? I used to wear regular glasses that were polarized. And sunglasses can be polarized also. Are your regular ones polarized?
What does that mean?
If you don't know, here's how you can test. Here's how you can test it. You need a phone that uses polarized glass or a polarized screen protector. My old phone, I used to have a protector on it that was like a matte finish, and it was a polarized screen protector that was on there. So I would look at the phone. If I was wearing my glasses or sunglasses and looking at my phone, I would see like a green-blue like tinge, like a haze on the top of it. And you'll actually see this like almost like a rainbow, but you're going to see like if you change the angle, you'll see the rainbow move and stuff. So if you don't know if your glasses are polarized or not, if you know that the phone you're using or the screen you're looking at is polarized and you look at it, you're going to see it to be like a rainbow behavior. This is really short. So if you could do it tonight, that'd be great also, but if you can't, have it done for sure for Thursday. So tonight, definitely 14-1. But this is also one question and some reading. Okay, so if you have time tonight, you can do it. Tomorrow is Thursday, you're right. So if not tonight,